Welcome to today's session. We'll be solving problem number 521, longest uncommon subsequence. This is a fascinating challenge involving string manipulation and algorithmic thinking. Let's dive in and explore the problem together. In this problem, we're tasked with finding the length of the longest uncommon subsequence between two given strings, A and B. A subsequence is a sequence that can be derived from a string by deleting some or no characters, while preserving the order of the remaining characters. For instance, the string ABC is a subsequence of EBC, but AEC is not, because the order of characters is altered. An uncommon subsequence, on the other hand, is a subsequence that is present in one string but not in the other. If no such subsequence exists, we return -1. The input consists of two strings, each with a length between 1 and 100, and they only contain lowercase English letters. The output is an integer representing the length of the longest uncommon subsequence, or -1 if none exists. Let's look at some examples. In the first example, the input strings are A equals ABA and B equals CDC. Here, the strings have no common subsequence other than the empty string. Because they share no meaningful subsequences, the longest uncommon subsequence is simply one of the strings in its entirety. So, the result is 3, which is the length of either ABA or CDC. This demonstrates that when two strings are entirely distinct, their longest uncommon subsequence will be the length of the longer string. In another example, the input strings are A equals AAA and B equals BBB. Similar to the previous example, these two strings have no common subsequence other than the empty string. This means the longest uncommon subsequence is again the entirety of one of the strings. Since both strings have the same length, the result is 3, which is the length of either AAA or BBB. This case reinforces that when strings are completely dissimilar, we can simply return the length of one of them as the result. Now, consider the case where the input strings are A equals AAA and B equals AAA. Here, the strings are identical, meaning every subsequence of one string is also a subsequence of the other. As a result, no uncommon subsequence exists, and we return -1. This highlights an important edge case: when the two strings are the same, there can never be an uncommon subsequence. Additionally, the problem's constraints remind us to handle various edge cases, such as when one string is a subsequence of the other or when the strings are completely unrelated. Careful consideration of these scenarios is crucial to solving the problem correctly. To solve this problem, we initially need to consider different approaches. The brute force method involves generating all possible subsequences for both strings, A and B. Once the subsequences are generated, we must check whether each subsequence is unique to one string and not present in the other. Finally, the length of the longest uncommon subsequence would be returned. While this approach is conceptually straightforward, it's highly inefficient. Since a string of length n has 2 to the power of n subsequences, this method leads to exponential time complexity, 2 and plus m, where n and m are the lengths of the two strings. This makes the brute force approach impractical for larger strings due to its prohibitive computational costs. However, analyzing this method helps us better understand the problem space, even though it's not suitable for real-world applications. Now, by observing the problem more carefully, we can develop a much more efficient solution. For instance, if the strings A and B are identical, then there is no uncommon subsequence since every subsequence of one string is also a subsequence of the other. In such cases, we simply return -1. On the other hand, if the strings differ, the longer string itself will always be the longest uncommon subsequence, as it cannot be fully represented by any subsequence of the shorter string. This leads to a much simpler solution where we only need to check if A and B are equal. If they are, return -1, otherwise, return the length of the longer string. This optimized approach is far superior to the brute force method because it eliminates unnecessary computations by leveraging key observations about subsequences. It operates in constant time, 1, since we only compare the two strings and calculate their lengths. Similarly, the space complexity is 1, as no additional data structures are needed. While an alternative approach could involve generating all substrings of the two strings and checking for uncommon ones, this approach is also computationally expensive and less efficient than simply comparing string lengths. Given these trade-offs, the optimized approach is the best choice. It directly addresses the problem requirements with simplicity and efficiency. By recognizing that the longer string, when the two strings differ, is inherently the longest uncommon subsequence, we avoid unnecessary complexity. This makes the solution not only elegant but also highly effective for this problem, ensuring correctness while adhering to the constraints. Ultimately, this strategy provides the most practical and optimal way to solve the problem. To start, let's understand the problem. We are given two strings, A and B, and the goal is to determine the length of the longest uncommon subsequence between them. A subsequence is essentially a sequence where some characters might be deleted, but the order remains intact. An uncommon subsequence is one that exists in either A or B, but not in both. If such a subsequence doesn't exist, we return -1. Now, the problem can be broken down into two main cases. First, if A and B are identical, then there is no uncommon subsequence because all subsequences of one string will also be subsequences of the other. In this situation, the answer is -1. Second, if the strings are different, then the entire string of one will not be a subsequence of the other. This means the longer string, or either string if they're of the same length, will be the longest uncommon subsequence. With this understanding, we can now formulate a simple solution. When the strings are different, the problem becomes straightforward. If A and B are not equal, the longer string cannot be derived as a subsequence of the shorter one. Therefore, the length of the longer string is the result. To implement this, we need only a few steps. First, check if the strings are identical. If they are, return -1. If not, calculate the lengths of both strings using the len function, and return the larger of the two lengths. There are some key insights here that simplify our approach. For example, the definition of a subsequence ensures that we don't need to explicitly generate all possible subsequences. This would be computationally expensive. Instead, the equality check and the length comparison suffice. This optimization keeps the solution highly efficient, requiring just constant time operations for comparison and length computation. The efficiency of this algorithm comes from its simplicity. Since the solution operates directly on the input strings, no additional data structures are needed. The strings themselves are used for comparison and length evaluation, minimizing memory usage. In terms of complexity, the time complexity is O(1), as we are performing basic operations like string comparison and length calculation, which are constant time. The space complexity is also O(1), because no extra space is allocated beyond the input strings. Now, let's consider edge cases. If both strings are empty, there is no uncommon subsequence, so the result is -1. If only one string is empty, the non-empty string is entirely uncommon, so its length is returned. When the strings are identical, the result is -1, as we've already seen. Lastly, if the strings differ in length, the longer string is guaranteed to be the result since it cannot be a subsequence of the shorter one. Let's walk through some examples to solidify our understanding. For the first example, with inputs A equals ABA and B equals CDC, the strings are not equal. We compute their lengths, which are both 3, and return the maximum length, which is 3. In the second example, where A equals ABC and B equals ABC, the strings are identical, so there is no uncommon subsequence, and we return -1. For the third example, with A equals EF and B equals AE, the strings are different. The lengths are 3 and 2 respectively, and we return the maximum length, which is 3. The final code implementation reflects this logic. It begins by checking if the strings are equal. If they are, it returns -1. Otherwise, it calculates and returns the maximum of the two string lengths. This concise solution ensures optimal performance while handling all edge cases effectively. This solution begins by checking if strings A and B are identical. If they are, it means there is no uncommon subsequence between them, so the function returns -1. This is because every subsequence of one string is also a subsequence of the other in such cases. However, if the strings are not identical, then the longest uncommon subsequence is simply the longer of the two strings. This is because the longer string itself cannot be a subsequence of the shorter string, making it the longest uncommon subsequence. The function accomplishes this check using the max function to return the length of the longer string. This approach runs in constant time, O(1), since it involves a single comparison and a length computation. This efficiency makes it well suited for cases where the strings are large or where performance is critical. This is the Java implementation for LeetCode problem number 521, longest uncommon subsequence I. The logic is identical to the Python implementation, with adjustments for Java syntax and structure. It checks if the two strings are equal and returns -1 if they are, as no uncommon subsequence exists. Otherwise, it calculates the maximum length of the two strings, which corresponds to the longest uncommon subsequence. Key differences include Java's use of type declarations and methods like equals for string comparison and math.max for determining the larger value. In this problem, we are tasked with finding the length of the longest uncommon subsequence between two strings, A and B. A subsequence is essentially a sequence derived by removing some characters from the original string while retaining the order of the remaining characters. The uncommon subsequence is one that is present in one string but not in the other. If no such sequence exists, we return -1. Let's take a look at the first example where A is ABC and B is def. Since the two strings are not equal, the next step is to calculate their lengths. Both strings have a length of 3. The longest uncommon subsequence in this case will simply be the maximum of their lengths, which is 3. Therefore, the output for this example is 3. Now, consider the second example, where both strings A and B are AAA. Here, the strings are equal, which implies there is no subsequence that is unique to either string. In this scenario, since no uncommon subsequence exists, we directly return -1. The output for this example is -1. This demonstrates an important edge case where the strings are identical, and the result is always -1 because no subsequence can qualify as uncommon. Next, let's look at another example where A is ABCD and B is XYZ. Since the strings are not equal, we calculate the lengths of both. The length of A is 4, and the length of B is 3. The longest uncommon subsequence in this case is the longer string itself, as it cannot be a subsequence of the other string. Thus, we return the maximum of their lengths, which is 4. The output for this example is 4. From these examples, we can observe a few key points. First, if the two strings are equal, there is no uncommon subsequence, so the result is -1. Second, if the strings are not equal, the longest uncommon subsequence is simply the longer string, as it cannot be a subsequence of the other. Hence, we return the length of the longer string. This approach is highly efficient, with a constant time complexity of 1, since it only requires a single comparison and length calculation. Overall, this problem is a good test of understanding subsequences and handling cases where strings are either identical or different, and the solution uses straightforward string operations to arrive at the result efficiently. The time complexity of this solution can be analyzed step by step, starting with the string comparison. When we use the equality operator to check if two strings are the same, the operation compares characters one by one. In the worst-case scenario, this comparison involves all characters of the shorter string, making it O, min, n, m, where n is the length of string N and m is the length of string B. However, if the strings differ early on, the comparison may terminate sooner. Next, we calculate the lengths of the strings using the len function. This is an O(1) operation in Python because the length is pre-computed and stored as metadata. Finally, the max function is used to determine the longer of the two strings. This comparison between two integers is also an O(1) operation, as it does not involve traversing the strings. These individual steps provide the foundation for understanding the overall time complexity of the solution. When these steps are combined, the time complexity is primarily influenced by the string comparison, which is O, min, n, am. However, since we are analyzing the worst-case scenario, where both strings are fully traversed, the overall time complexity can be expressed as O, n plus m. This ensures we account for the lengths of both strings in the analysis. Shifting our focus to space complexity, the solution is highly efficient and uses only O(1) space. First, the input strings at and b are passed directly to the function, and no extra memory is allocated to duplicate or modify them. Second, the algorithm relies on a fixed number of variables, such as those storing the lengths of the strings and the return value. These variables require constant space. Lastly, the solution does not involve creating additional data structures like arrays or hash maps, which minimizes memory usage and keeps the space complexity constant. This constant memory usage leads to a space complexity of O(1). To better appreciate the optimized approach, let's compare it with a brute force method. A naive solution to finding the longest uncommon subsequence would involve generating all possible subsequences of both strings. This would take 2 to the power of n time for a string of length n, as each character can either be included or excluded from a subsequence. After generating these subsequences, we would then compare them to determine which are unique to one string and find the longest among them. This approach has a time complexity of O(2 to the power of n plus 2 to the power of m, which is exponential and impractical for large inputs. The optimized solution avoids this by recognizing that if the strings are unequal, the longer string itself is the longest uncommon subsequence. This eliminates the need to explore all subsequences and ensures the operations, comparison, length calculation, and finding the maximum are efficient. Together, they result in a final time complexity of O(n plus m), making the optimized solution drastically faster than the brute force approach. When solving the longest uncommon subsequence problem, there are a few common mistakes to be mindful of. First, not accounting for edge cases, such as when one or both strings are empty or consist of a single character, can easily lead to incorrect results. Always validate these scenarios explicitly to ensure robustness. Another pitfall is using an inefficient brute force approach, such as trying to generate all subsequences of the strings. Since the number of subsequences grows exponentially with string length, this is computationally prohibitive for larger inputs. Instead, look for optimized techniques that simplify the problem. Additionally, it's important to remember the distinction between a subsequence and a substring. A subsequence can be non-contiguous, whereas a substring must be contiguous. Confusing these concepts can lead to flawed logic. Lastly, some solutions fail to properly compare unique subsequences, mistakenly assuming that any non-matching substring is unique. This oversight can result in missed cases where overlapping subsequences are not correctly handled. Another mistake to avoid is overcomplicating the problem. Some solutions introduce unnecessary complexity, such as using extra data structures, when simpler methods, like focusing directly on the string lengths, can solve certain variations more efficiently. In interviews, understanding the problem scope is crucial. For example, clarify whether the task involves substrings, subsequences, or both, as this distinction will guide your approach. Also, consider the constraints. If the strings are very large, brute force solutions become impractical, so you might need to explore greedy or dynamic programming techniques to reduce complexity. Look for patterns in the problem. For instance, if one string is longer than the other, it cannot be a subsequence of the shorter one, which simplifies the logic. Lastly, during interviews, clear communication is key. When discussing your solution, explain the trade-offs between brute force and optimized methods. Interviewers value your thought process and clarity just as much as the final solution. To deepen your understanding, it's helpful to explore related problems. Longest uncommon subsequence I, or LeetCode 521, centers on finding the longest uncommon subsequence between two strings. A natural extension is LeetCode 522, which expands this concept to arrays of strings, adding complexity. Another important problem is LeetCode 1143, longest common subsequence, which is foundational for building a solid understanding of subsequences and often serves as a prerequisite for tackling related challenges. Finally, LeetCode 392 is Subsequence, teaches efficient methods for checking if one string is a subsequence of another. These problems are interconnected, and working through them provides valuable insights into various techniques and optimizations that can be applied across subsequence-related tasks. To solve the problem efficiently, there are several alternative approaches to consider. One of the simplest and fastest methods is the optimized comparison approach. Here, instead of generating subsequences, you first compare the lengths of the two strings. If the lengths differ, the longer string is automatically the result, as it cannot be a subsequence of the shorter string. This approach has a constant time complexity of O(1). For more complex variations, dynamic programming can be used. By building a DP table to calculate the longest common subsequence, you can then determine the uncommon subsequence. This method typically has a complexity of O(n*m), where n and m are the lengths of the two strings. A greedy approach is another option, particularly for problems like is subsequence. In this case, you iterate through one string while checking characters against the other, achieving a time complexity of O(n plus m). For problems involving arrays of strings, such as longest uncommon subsequence 2, you can use sorting and filtering. Sorting strings by length and checking subsequences iteratively can be effective, though it has a higher complexity of O(n squared asterisk m). Each of these approaches is tailored to specific scenarios, so choosing the right one depends on the problem constraints and requirements. Great job completing this problem. We reviewed the brute force idea and how optimization plays a key role in solving the longest uncommon subsequence I. Remember, practice is the key to mastering these problems, so keep going. Thanks for tuning in, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!